Hello, everyone. We are the Stanford Machine Learning Group, and our paper is MedAug, Contrastive Learning, Leveraging Patient Metadata Improves Representations for Chest X-ray Interpretation. Recent work in self-supervised contrastive learning has improved learning of meaningful representations from unlabeled data for downstream image classification tasks, including chest X-ray classification. Contrastive learning is enabled by contrastive loss functions that are optimized when positive image pairs are given similar representations, while negative pairs are given different representations. In previous contrastive learning work on medical imaging, positive pairs are defined as transformations of the same input image, and patient metadata has not been leveraged to improve the selection of positive pairs. Here we use patient metadata to improve the selection of positive pairs in contrastive learning for the downstream task of pleural effusion classification in chest X-rays in the CXR dataset.
Here we present our method. Given an input image X, in order to form a positive pair, we choose the first image by applying a transformation to X. Then we collect all the images from the same patient and restrict them to a criterion C. This forms a set of available images as C of X, from which a second image is sampled and transformed to form the positive pair. The loss function is defined using standard contrastive loss, where the transformed image x1 delta and x2 delta form the positive pair. In the CXR data set, each patient may have multiple studies, and each study may have multiple images. The images can have different lateralities, frontal or lateral. Labels are provided at study level, meaning each image within a study has the same label. We experiment with different criteria, for example, the second image in a positive pair. C of X always comes from the same patient as the first image, but we further vary the criterion C to same study, distinct study, or all studies. Under the same study criterion, we further divide the criterion into same laterality, distinct laterality, or all lateralities.
Here are the classification results from linear fine-tuning and end-to-end fine-tuning of the pre-trained model that was obtained from each positive pair selection strategy. Our metadata-based strategies that allow positive pairs to include images from the same study, highlighted in green, resulted in improvements over the baseline, whereas the strategies that allow positive pairs to include images from distinct studies, which are highlighted in red, do not result in improvements. The best result is obtained when defining positive pairs as images from the same patient, same study, regardless of laterality. This makes sense because labels in this dataset are defined at the study level. Also, adding a random crop augmentation from MoCo V2 to the same patient, same study strategy results in our best pre-trained model that significantly outperforms baselines.
We developed a method to use patient metadata to select positive pairs in contrastive learning and apply it to chest X-ray classification. Our best strategy achieved a performance increase of 14.4% in mean AUC compared to the ImageNet pre-trained baseline, showing that using patient metadata to form positive pairs can notably improve pre-trained representations. Our experiments also indicate that increasing the number of distinct images selected to form positive pairs may improve pre-trained representation. Thank you for listening.